Okay, so hello everyone, good afternoon. I think I already attached the your quiz result on Google Classroom. If you want to check, you can check your Google Classroom. I shared the folders, and inside the folders you can find a PDF, and you can find your name based on student ID. Okay, your student ID. I think there is one mistake in answer key, but I already fixed that. So your final score, I think, in general, is higher than your results. Okay. For example, if your result is 70, your final result will be maybe 74, or maybe if your result is 74, your final score will be and I also test the answer key, and I think because I haven't had a chance to make another video, so I hope my my notes is enough, okay, for you. Okay, if you still need some maybe discussion regarding the quiz, or maybe you want to find or maybe asking more details uh, for those questions in quiz, we can have it in class if you have time, and maybe you can maybe discuss first with me with which one you need to have a more discussion. Okay. Um, for today's class, actually, I will uh, explain a little bit overview about the indeterminate forms. Okay, and maybe something that I missed out on Tuesday class. So I will maybe make some explanation for today. And the second part for today will be 4.7, the optimization. Okay, the optimization. Okay, so yeah, that's attendance. Okay, first of all, let me explain a little bit about the feedback. Okay, so I think the first question is not too complicated. This is basically when you uh, move the e to the bottom equations, and it become a fraction that is infinite over infinity. And when it's happened, you can take a L'Hopital process, and you derive the top equation, derive the bottom equations, and check the equations. And I think we can simply say that it will be resulting 0 in the answer. Okay. And then, yeah, I think most of you did a good job here. Okay. Okay, I think no question here, right? I think it's understandable for first question. Okay. Okay, the second part, this is having a tangent with power of x, the tangent to x with power of x. It's 0 with power of 0. So it's also, we call this is indeterminate, right? Indeterminate powers, right? Or we can just general say indeterminate forms, okay? But the idea now, in my case here, okay, I'm writing the whole equation tangent with power of x with terms e, and then evaluating this limit on the top. But if you want, you can make separate the equation and make maybe let y equal, and then you can do this ln y, and you should solve this first, take the limit, and then solve with L'Hopital rule, and then at the end, still you need to power this e so that we can have the evaluation of y. Okay, so it depends on you. Depends on you which method, but I think it's still the same. But I want to write here for my case here. It's directly I'm having this e, so I'm evaluating the top equation here. Okay, and remember, because it's e, when you have limit and then it's e, you know that e will be positive functions, right? So it's not really uh, necessary to put limit here. We can just limiting the top equation because this is the one that has uh, the one that we need to take L'Hopital, right? So if we look here, we have x, ln tangent to x. Okay, this is the 0, infinity. If we check with 0, okay, we check 0, x is 0, ln tangent becomes infinity. Okay, remember in ln, okay, uh, okay, this is the one that you need to think or keep in mind in ln, or maybe better if you remember how to graph the ln. Okay? This is important. Okay, so whenever you have the ln, it will goes down here, right? If we have the uh, approaching 0, right, closer to 0 from here, and it's going infinitely negatively large. Okay, so when we have here, this is we call this indeterminate product. The principle, most of the indeterminate forms is the idea will be we make it into 0 over 0 or infinite over infinite. Okay, that's the principle on L'Hopital rule. So by doing that, we take L'Hopital, take 1 over x here. If we check, this will be infinity and infinity, right? So 1 over x become negative 1 over x squared. And ln tangent to x, okay? We have some chain rule. Ln become 1 over tangent to x. And tangent to x becomes secant squared to x multiplied by 2. And I will write 2 here. So 2 over tangent to x multiplied by secant squared to x. So right here, so chain rule here. Okay. This is a little bit review on chapter 3. So actually, okay, uh, if I say a midterm or maybe a final exam, for example, it doesn't really necessary. Okay, maybe final exam chapter this. In calculus, usually you need to think all of them in one case. Like for example, this one here, you need to apply all the rules that you learned before, right? So that will be the case in calculus. And another suggestion from me is in the next semester, or maybe if you take another advanced mathematics lesson or course, the one that you have learned, probably you will be, maybe some part of it you need to still use it, okay, in the future. Okay, so after you pass the course, you don't forget to always check when you are in the future, okay, doing another course. Sometimes some part in this calculus will be still you need to have. Okay, you need to at least remember how. Okay, okay. Now chain rule we have here, and take a rewrite the form. Okay, let me move here. This is the form. Okay, okay. So actually I can write negative 2x squared secant squared to x and then tangent to x. Okay, and then if you see the secant squared, I can change to 1 over cos squared, right? And tangent to x, I can change to sine 2x over cos 2x. And I can remove this cos 2x with this because it has the square. So I will cancel the cos, and then the final result will be this. Okay, the final result will be this: negative 2x squared over sine 2x multiplied with cos 2x. Okay. Okay. Now the idea here is remember I think in the limit part, chapter 2, we have sine x over x, or x over sine x. It's the same result. It will be resulting 1. It will be resulting 1. It's we call the trigonometric limit identity. Okay, this is very basic, that we need this to make our derivative of trigonometry proven. Okay, we need this limit. Okay, so this is equal 1, and this is equal 0, right? And because 1 and 0, then it's 0. So eventually you will get e with the power of 0. It's 1. Okay. Sometimes, uh, when you check some exercise with L'Hopital, maybe I will give you maybe tonight or maybe tomorrow, just a list of questions that you can solve. Okay? I'm not giving as an assignment. Okay, so you can check, and sometimes most of the results will be e with the power of 0. But you need to see what kind of questions. Okay, you can make some simple conclusions, but uh, it's most of the case, but not all cases. Okay, not all cases. So e with power of 0 equal 1. Okay, so that is the answer, 1. Okay, I think you were also good job here. Okay, so that is the overview for last Tuesday feedback. Okay, okay, to start for today. Okay, maybe before we move, uh, any questions? Any questions? Maybe online students, any questions? Okay. If no, I will move to the next section. Okay. 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 We start with this. Okay. We start with this. I have 3 different limit here. It's the same similar form. Okay. But different in some aspect. Okay. But the form is I think a little bit similar. It has a power of x, and it has something 1 over something here, x squared. This is ln 4 divided by x. This is 1 over ln x. Okay. Okay, let's try. Maybe I will give you a few minutes for you to try. And the idea still similar with the last feedback, the tangent with power of x. So that will be the idea to solve. Okay. So let's check whether you can find the answer or not. Okay. And of course, if you want to check, okay, if we take this infinity, take inside, all will be given the same form, right? Take infinity here, something over infinity is 0, some constant 0, 1 infinity. Okay, this also 1 plus 0 infinity, right? 1 plus this is also 0 and infinity. So all will be having the 1 with the power of infinity, right? So that's why I thought previously on Tuesday class that 1 with power of infinity in limit, this 1 is not exactly 1. Okay, maybe it's 1 something, or maybe 0, almost 1. So it's not exactly 1, or it's not the base of 1, not the base of 1. And this is the example. And if you check the answer, these 3 limit will have different answer. If you check, okay. Okay, if you have calculate, maybe you can show the results. Okay. Yes, 4. Can also check the other one. Yeah, the one of the answer is 4. Okay, maybe giving you the uh, the solution for this one here. Okay, maybe we can let the sum y, okay, y equal with the inside function 1 plus ln 4 over x, and this is the power of x, and take the ln. Also, we can write x ln 1 plus 4 over x. Okay. Okay, let's take the limit. For limit, let me just write for this first. Okay, x ln 1 plus. Okay, if we check here, this will be uh, the uh, the indeterminate products, right? This is indeterminate products, infinite and then 0, right? So probably we take the x to the bottom so that we have 1 over x. Okay. Now if uh, we check the condition here. This is 0 over 0, right? ln 1 and then ln the 1 over infinite is also 0. Okay. Okay. Remember, if you have ln and then a constant, this is a constant. A constant. Okay. And also remember, if you have e also a constant, okay, not a variable. Okay. So this is 0 over 0. We can do L'Hopital. We can do L'Hopital here. So L'Hopital rule, and we can simply derive the bottom one is just 1 over negative 1 over x squared. And this part will be, let me write one by one here, 1 over 1 plus and 4 over x. And then we need to have the chain rule. So this will be negative 4 divided by x squared. Okay. This is from the ln 4 over x. Take derivative, it's basically derivative of 1 over x, and then multiply with the ln 4. This is negative ln 4 over x squared. Okay, rewrite this. Okay, rewrite this equation. Let me take the take the 1 plus ln 4 going down here, and this x squared going up here, and then multiply with the ln 4. So this will be negative ln 4. Let me write all here so that this is cancelled. Okay. So I will have now negative. Oh, sorry, this is negative, so negative also cancel. So ln 4 divided by 1 plus ln 4 over x. And we can check that ln 4 over x is 0 because of infinity here. So ln 4, 1 is ln 4. But remember, this is ln y. Okay, this is ln y. So this is ln 4. So ln y. So y is e with power of ln 4, or this is 4. Okay. Okay. I will leave the 2 questions for you to solve again with the similar method with this one, and you will see that it will have different answer. Okay, so this one having 4, the other one will be a different result. Okay? So this is the case for 1 with power of infinity. Okay, why it's indeterminate forms. Okay. Okay. Any questions? Any questions from here? Okay. Okay. So these 2 questions, I'll leave these 2 for you. So 1 plus x squared with power of x and 1 plus 1 over ln x with power of x. All right. Okay. If there's no question, I can move to another problem or some additional notes for you. Okay. 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 The next thing is, okay, let's say we have, let me write, suppose f is a positive function. If limit as x approaching a of f of x is 0 and limit of gx is infinity. Okay. Now this is the form that not really have been explained before. So if you look here, it seems it's indeterminate powers. It has 0 here, right? And it has infinity. Okay. So we are going to see that whether it is the indeterminate forms, or we can just simply say that it will be 0. Okay, it will be 0. Okay. So first, as a starter, we can simply let's say y equal f of x. Let's say we have this y, okay, to help. And then, like how you solved the problem before, let's try using some ln here. Okay, okay, because f is a positive function. Okay, let me write here a positive function. So we know also know that the we can define, so ln of x is defined. Okay, now remember the ln graph. Okay, I think it's better to explain you with graph rather than the words. Okay, so because f is positive function, okay, and when you have limit, okay, limit of f is 0, x approaching a. Oh, I need to write the limit first. Okay, sorry. So we need to write the limit as x approaching a of the ln y, and then limit x approaching a of the gx ln f of x. Okay, because f is a positive function, okay, and limit for the f is 0, so we can say that this is actually going to have ln 0, right? So you can say that it will. We can say that this part here, this is we are saying that the limit is approaching 0, okay? Approaching x to 0. Okay, got it? So ln, because it's positive functions, we can define this, and if we check with the graph for ln, so we can see that. Okay, so let's say this is our graph. Okay, so ln. So when we say limit as x approaching 0, okay, because we know that this is positive function, and ln uh, the f for limit xa, or maybe I'll write here too, so that you will confuse them. So limit, this is 0, right? Based on the information at the beginning. So we check that this is 0. So we can say that this is actually limit of x approaching a for ln fx. We can say this is ln, that is the x is approaching 0, or the f here approaching 0. So if we look here, when we are going to have 0, okay, when we are going down, it's going to infinity, but negative, right? Okay. So we can say that this will be negative here, negative. Okay. So we can conclude, okay, okay, this part here will be a negative infinity. Okay. Remember that this g from the information is already positive infinity, but because of this ln, when we have the property of ln, it will be having a negative infinity. So, okay, so because it's negative, okay, let me write here again to take some notes that this is equal to infinity. Okay, so the result will be negative infinity. Okay, now what can we conclude from here? Okay, so let me write limit as x approaching a of ln f of x is negative infinity. Okay, if, okay, maybe here. So if we say Maybe another variable we take t. I think t is on y. Okay. We can say that limit as x approaching a of y. Okay, then we take back to the very first equation there. This will be resulting limit as t approaching negative infinity of e with power of t. Okay? Or if you want to maybe slowly, you can see from here that is e ln y. Okay, this is y. This is to saying that if you are going to check this limit, okay, if you're going to check this limit, uh, limit, let me maybe write the original one. We check this limit, okay, with e, and then this will be g x ln f of x, okay. So if we have this, we take the limit, okay, we take the limit here, and this is negative infinity, okay. Remember when we have a negative infinity for e, okay, for e, we can say that this is what is happened, right? For negative infinity. Okay, this is just use logic first. Okay, we see this negative here. This is, we can say, 1 over e with power infinity, or we can say 1 over infinity in limit is 0. Okay, so it's already proven that, okay, when we have this, uh, the limit as x approaching a for f of x, if f of x is 0 and then this g is infinite, we check from previous one, it resulting, the limit will be having a negative infinity. Okay? And because it's in e, so 1 over this e, this big E, then it will be 1 over infinity. Okay, so it is actually going to have 0. Okay, so we can say that this, okay, is what we have done. Okay, if you want to simplify with some t, okay, and or if, okay, if you can also write in, you can also look at this. Let's say this is e, okay, e to the x, okay, e to the x. Okay, e to the x is precisely, it's going to have large and large and large and going to positive. Okay, if you have a negative, okay, if you have a negative, yeah, maybe, yeah, I think, okay. So this will be e with negative x. And you see, if x is going there, so you can imagine as x is infinity, okay, it's going to go to 0, right? Going to have to almost touch this x-axis 0. Okay, so this is actually what is happening with this with 0 here. Okay, so you can look for the visual. Okay, imagine how the x changing. Okay, or you can look at the result here. You have the negative infinity as your result from previous calculations, and you have e. It's simply, we say 1 over e with power infinity, and in limit this will be 0. Okay, I hope you You got my point. Okay, you can see from the number that you calculate, or you can prove with the graph, with the graph, with the graph. Okay, I hope you get the point. So proven, okay, that the limit as x approaching a is 0. So when you have it seems the indeterminate forms like this form here, then we can prove that this is actually going to have a 0 result. Okay, let me maybe if you want to take maybe from the beginning, okay, maybe this first, okay, so that you can have a few maybe bigger, maybe this big. So this is the information or the assumption that we make. The f should be positive, okay? So should be positive function, and we already defined the information is the limit of f is 0, okay, and the limit of g is infinity. And the problem is if we have this f and then power of g, it seems that this will have 0 with power of infinity, and it seems it's indeterminate. Okay, so we are having it seems that it will have the 0 with the power of infinity, and we need to know whether we are having 0, okay, or any result from here. And from what we have done, okay, from what we have done, you can see here that because f is a positive function, then we can define this ln f. Okay, we can define this as our usual ln. Okay. And then when f is 0, then we can say that the ln 0 is like when it's going to have uh, approaching 0, and then it's going down. Okay, so the results for the limit will be having a negative infinity. Okay, and then this is the conclusion. Okay, the conclusion. Okay. Any questions? Okay. Okay, any questions? Okay. Sometimes if you check the questions in the textbook, some sections or some chapter, sometimes the question is not only asking uh, the results, right? Sometimes it's asking how to prove or proving some equations. Okay, it is one of them, actually one of them from the textbook. So yeah, I think university is having more explanation about the process. Okay, instead of just the final results. Okay. So in maybe a physical exam, like maybe this calculus exam, uh, different from quiz. In exam or midterm or final, sometimes the question will asking you to make some proof or to show some process. Okay, so it's not only to find the correct answer. Okay, something is to also show the process. Okay? And sometimes, even though you didn't get the correct answer, if your process is correct, your first step, second step, third step, it's already okay, you still have a point, and you still have a point, because that is one I want to look for. Okay? How you look and how you observe, how you process, how is your process. That will be your points. Okay. Instead of you didn't really show the process, like maybe you're going like circling, even though you find the final result, maybe it's not like really a full point either. Okay? It's not a full point either. So if you want to have like a perfect, then you need to show the process and also get the correct answer. Sometimes mistake can happen, like you mistake the plus with minus, or sometimes plus multiply by minus, and you still write plus. It's happened, and that is human error, not really a big problem, not a really big problem. Even though maybe the correct answer is 1 and you miss out this 1 as -1, I still give much credits for the points. Okay, so please make sure you emphasize the process in the answer. Okay, I'm not sure on your high school whether the exam is a typical like answering with process, or just giving answer and then it's okay. Usually, when you go to university, you take maybe exam, right? Some exam, and maybe it's just options, right? Or no, options, right? Usually, most of the question is options, right? Because it is needed to select from many students, right? It's too many students. Okay? But in class, maybe 50, 60, maybe some teacher want to look for the process. Okay? Like myself, I need to look for what is the process. Okay, okay, that's the additional notes for the L'Hopital rule. Okay, I will end the L'Hopital rule. Okay, this will be the end of L'Hopital rule. The rest, I will give you some questions, and maybe if you have some difficulty, you can ask me or ask your TA, or maybe your TA will also give in uh, the TA session, and I will have maybe some video if I have time. But I think I will make video after I finish the optimization. Okay, so we move to another section called optimization. Okay, okay. This is 4.7 optimization. And I think this is one of the application of calculus that you can actually apply, but sometimes you are not really applying it. Okay, okay. Let me give you a few notes on this optimization. We can start with. Let me check first. Okay, some notes. Okay, so during this optimization, first you will have a situation, a problem or condition. Okay, you have a case, okay, or a problem. Okay, that is related to critical point. A second, to understand the problem, sometimes you need to draw a diagram, and also name the variables. And the third, find relation or formula or models that is fit with the case, okay, that is suitable for the case. And then the last part is you need to find max or min value through the f prime x equals 0. So this is 4 points that I summarized from the textbook. Okay, So if you remember the related traits, okay, the problem that we have in chapter 3, this is similar process. Okay, so you will have a situation. You read the questions first. You read the problem, and to imagine the problem or to understand the problem, sometimes you need to draw. Okay, maybe you need to draw like an area or maybe some object. Okay, and then you need to name variables. Usually, you will take the area, volume, closest point in graph. Okay, so distance, area, volume, yeah, and then you have the variables, you have the diagram, then you need to think what models that fit. Okay, maybe you need to find the area, and then or maybe the area is the model that's suitable, and then after that you need to take derivative and check the f prime equals 0 to check the critical point and to check max or min. Okay? Whether it is sometimes you need to ask the question asking what is the largest possible area, blah blah blah. What is the smallest, blah 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 blah. Okay, that's the typical question. So I think we better go to some example. Okay, some example. Let me give you an example. Maybe start with a simple example. Okay, if uh, 1/200 centimeter cube of material is available to make a box with square base and an open top. Okay. Find the largest possible volume of the box. So we start with this simple one with the box. Okay, so you have the 1,200 centimeter square. It's the material. So it's like when you want to make you make a box, maybe your school project, and then you want to cut the area, and then you need to make sure, okay, we need to have the largest possible box from the area. Okay, and sometimes you draw the the, the paper with maybe the diagram, right? How you fold the paper, right? Okay. But actually, before you start, you can calculate first, okay? And then imagine how uh, the distance, okay? How the value will be. Okay, so because it's already make sure that it's a box, but it's also have mentioning the restriction. It should be a square base. So the base that in the bottom will be square, and the top is open. So there's no top. Okay, no top, open top. So this is the number of material that's available, and you need to make a box. It's square base and open top, and it's asking the volume. Okay, so the largest volume possible. So first, okay, maybe we can draw the box first. We can draw the box first. Okay, maybe like that. Okay, and then let me make it. Okay, and we need to take the base is having square, right? Maybe same variable here, maybe x and x, okay? And the other one will be maybe y, okay? Okay. Because it's not saying the box is a cube, right? Not a cube. It's just a box. The square is the base. And this is no top, right? Open top. It's open. Okay. Now we have the materials is 1,200. This is the area, right? So we need to plus all the possible area and make it into first the formula for the area. Okay? Formula for the area is the x squared, right? And then plus the xy, 1, 2, 3, 4, for 4xy. But because it's top, so that's just it, right? So plus 4xy. Okay. The second, we want to find the volume. The volume from this the box is the x squared and then y. Okay. Now in optimization, okay, because we want to optimize the volume, we want to find the largest possible for volume. We call this is our optimized, or we can call this our optimization. Okay. The area here we call this our constraint. Okay. And all optimization problem will be having these two kind of formula. Okay. The first one, the optimization, is the one that is our goal. We need to find the largest volume, right, based on the question. It's called, this is our optimization, the one that we need to take the optimum result, right? And this one is our constraint, our restriction. We have a limitation of this number 1,200 to make the volume, right? So we call it our constraint. And all this case in the optimization is you need to find these two. You derive this, and you switch. Sometimes you substitute x and y based on this 1,200. Okay, so as simple as that. I think this is pretty similar from what you have done before in maybe high school or junior high. Okay? But now, since we already learned calculus, we will take this optimization with some terms from calculus, and maybe the problem will be a little bit complex than this one. But basically, this is how we solve the optimization. Okay. Okay. Let's resolve this first, and let me just give you another example. Maybe I think we can have maybe 3 more examples. I think if we have time. Okay. So first, okay, maybe we can take the constraint to see the x squared plus 4xy equal 1,200. Okay, maybe we can take this as this, okay? And then maybe we can take the y will be 300 divided by x and then minus x divided by 4, okay? We can take this as our y, okay? You can also check with x, but I think better with y. Okay, I think I need to go to the next slide first. Okay, so y is 300 divided by x minus x power over 4. And then we have volume is x squared y. Okay, we can check the, or substitute dy, x squared, and then 300 over x minus x over 4. And the volume will be 300 x and then minus x cubed over 4. Okay. And to find the largest possible or maximum value, we need to find the critical point, or we need to derive this. Okay, derive. So take the derivative, first derivative. So let me write the v prime will be 300 minus 3x squared over 4. And this should be equal 0 to find the critical number. The critical number, we can take the 3x squared over 4 equal 300. Then the x squared will be 400, or the x will be plus minus 20. And because this is, the result should be in positive because that is the one that we need, right? So we take the positive, and we take the positive. So x should be 20 centimeter. So the y will be 300 divided 20 minus 20 divided by 4, and this will be 10 centimeter. So our volume that is largest will be 20 squared 10, so 4,000. Okay. 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 The next question that I will give you is something that maybe every calculus students, when they learn the optimization, maybe they sometimes they didn't notice this phenomenon. Okay, I will give you one question or one phenomenon. Okay. 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 Maybe online students. Any question? I think you get the idea for this optimization, right? Okay. Okay. Let me move. Okay. Let me move. Give you another question. Okay. I think this one is easy enough to understand how the optimization works. Okay. How it works. Okay. Next will be another example will be about the wire. Okay. So let's say we have a wire with length, let's say 1 meter. It's cut into two pieces. Each piece encloses a square. Okay? So you have a wire. You cut the wire into two. Each wire you can make a square. You make a like a rounded square, and then find the largest area enclosed. So you need to find the largest square possible, from this wire. So it's cut into two. So not necessary to be half. So that will be your variable. So 1 minus x or You can name your own one variable and see what is wrong with this question. See what's wrong with this question. And this is, I think, almost calculus student didn't notice this problem. So let me give you a few minutes to think, and then maybe try your best to check, okay, to check and solve. And for online students, if you have some calculations, maybe you have some number, you can write in the chat box what's the number. Okay. So after you cut 2 to make square, then the side will be divided by 4, right? To make it the same square, right? Okay. So that's the idea. Okay, Rion, good thinking. Okay, good thinking. This is sometimes the majority of the students didn't think that. Okay. But still, I think, Rion, if you think on, yeah, the critical point is minimum. That is the actually one way to think. But if you think using limit, still this largest possible can be answered, but through some assumptions. Through some assumption. But in general cases, your thinking is correct. Your thinking is correct. For general cases, this will not asking the largest. Okay. Good point, Priyan. Okay, maybe helping you with the drawing. Okay. So let's say this is the wire. Okay. The wire. So the wire will be having 1 meter. So 0, 1, right? And then cut. Maybe cut in maybe here. So this will be x, and this will be 1 minus x. Okay. The first square for x will be x over 4, x over 4. Okay. And this one here will be 1 minus x over 4, 1 minus x over 4. So the area between these two will be x over 4 squared, and then plus the 1 minus x over 4 squared. Okay. I think this is should do for the formulations for the area. Okay. So we have the constraint already done in this wire, right? It's 1 meter and 1 minus x, and x as the pieces. So this is our constraint, and this is our optimizations, right? So if it is asking, for example, the critical point, then we can check the first derivative like we used in previous example. So we can just derive this and make this 2x over 4. So this will be x over 8 minus 1 minus x. 1 minus x over 8. Right? 16 divided by 2, yeah, 8. Okay. So this will be having 8 and then 2x minus 1. Okay. And if we check the 0 here, our possible x or our critical point will be, it seems is half. Okay, it seems is half. And then if you are doing this, okay, you get the x is half, so then you get a half, and then you check the result. This will be 1 over 8 plus, okay, 1 over 8, okay. This will be 1 over 32, or 2 divided by 64, so this is 1 over 32. And then you write, okay, maybe you write the answer on your test. The maximum area is 1 over 32. Okay. It seems okay, right? It seems okay. Do you think it's okay? You think it's okay? What's wrong with this? Can you pinpoint what's wrong? I think for online students, you got the point there. Okay, for this classroom. Yeah. Yes. Yes. So this is actually not a maximum area. This is the minimum area. So if you check your textbook, check the question in optimization. The question in your textbook is already correct. Whenever you have like finding the max, finding the mean, they already asked the right question. But this question here, it's not asking the right question. It should be find the smallest area possible. So I'm just changing this into largest. But how do we make sure? How do we confirm this is minimum or maximum? Remember your previous sketching curve. Sketching curve. Okay. So we have a critical point here. 1 over 2. Okay. We check 1 over 2. We check 1 over 2 in our graph. In our graph. Or we can check with the first derivative test in line number. We can check this and check this. This may be half. And because this is, let's say from 0 to 1, because the wire is 1 meter, right? So let's say we have a 0, 1 in the line number here. So based on first derivative test, we can look from here. Okay, this is positive, so we can just see this 2x minus 1. If we have maybe some number here and some number here, maybe 1 over 4, we can check 1 over 4. It will be a negative, right? It will be a negative. And if you check the between 1 over 2 and 1, maybe 3 over 4, so that I can cancel with 2, we see that it's positive, right? It's positive. Okay, we change this 3 over 4. Oh, it's positive, right? So it's positive. So what is happening here? The slope going down and going up. And we know that from previous sketching curve, it's local minimum, right? It's a minimum. So this is a minimum. Okay. So this is what's happened when you are changing the question with it should be the minimum, the smallest. We change it to largest. This is what happened. Okay. So still, I want to answer the largest area possible. Okay, I want to answer that. Okay, if we make some assumption, okay, this is just for fun, okay, just for fun, okay, we make for fun here. We can make some answer like this, okay, as limit, let's say approaching x to 1 from the left, okay. So we check with limit of our functions, okay, of our functions, which means we are going to have 1 in the, where is, oh, here. So if we have 1 with limit, okay, with limit, okay, if we have 1, this will be 0, right? This will be 1 over 16, okay, 1 over 16, 1 over 16. If we have limit here, check limit to approach 0 from the right, okay, and checking 0, this is 0, this is 1 over 16, right? Okay. I can make some argument here that the limit, if it exists, okay, if it exists, I can argue that the max area will be 1 over 16. But of course, if you apply this in the real world, it's not really happening, right? It's not really happening because if you are using solid calculation, you are actually cutting 0 wire or almost 0 wire and make it the one that is the bigger one. Of course, it will be 1 over 16, right? So it seems it's not possible, but in the terms of limits, it might be possible. So the maximum area will be 1 over 16. But the truth is, the true question from this truly the smallest possible area is 1 over 32. Okay, this is the true questions, the true finding the smallest possible area. So I just changed this questions to check whether you understand the optimizations, and then to see the review, a little bit review of the first derivative in the first derivative. Okay. 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 So yeah, with limit, you can assume that it might have the maximum value, but of course, probably in real life, that is seems impossible to happen, right? Okay. Okay, but don't worry. Okay, don't worry. In your textbook, all the question is the right question. So so if it is asking the minimum, it's already asking you like maybe find the smallest possible. So that means that okay, it's already minimum. So you just need to think, finding the critical point, and then find the answer the value. Okay. Okay, I already see the question, and all the question is I think the right question. Right question. This is just uh, to review the first derivative and to check this that this optimization is actually our first derivative application. First derivative application. Okay. So maybe today, maybe 2 example, I think more, and maybe next week we can have maybe another example, and then some some concept from uh, or maybe some notes for Newton's method, and the last part in chapter 4, I think, for next week between Tuesday and Thursday. And if we finish that, let me check the. It's now is 18, and let me check. So 18. So hopefully, uh, 23, 24, and 25, 30. Okay. So probably between, I think, I can offer you the midterm between 30 of November or uh, December 2nd. December 2nd. Okay. The positive or negative between these dates. If you have 30, then it's, yeah, you'll be early on the midterm. Uh, December 2nd, you can have some maybe some TA session before the Tuesday. So it's up to you. Do you want to Tuesday or Thursday? 30 or December 2nd? Or okay, it's up to up to me. You think both okay, right? You think both okay. So if we have the Tuesday, then the TA on the previous week will have to review, prepare for your midterm. Okay, okay. I think that will be okay. Okay, okay, guys. The online students. Okay, I hope you listen. We already taught in the student in the classroom, and I think 20, not 20, 30, November 30th will be the our midterm. Okay, so we will have next week finishing the chapters, uh, and then I hope on the last day, next Thursday. Next Thursday is 25, right? So on 25, I hope I have maybe 30 to 40 minutes, some practice for some questions that I think may be important for you. Okay, or maybe I will show you the last year or last 2 years midterm, or some from midterm or final. Okay. 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 Let me give you another question here. Okay. Okay. A cylinder has a fixed volume. This is not really having any number, but just mentioning it has a constant. It's just asking what ratio between radius and height, minimize the surface area. Okay. So you need to write the ratio between radius and height. So you need to write what is R over H, okay, when the cylinder is having a constant volume, fixed volume, and it minimizes the surface area. Okay. So it's already correct. Correct questions. It's minimized. It's minimized. Okay, now you need to a little bit reviewing what is cylinder and what is the volume of cylinder and what is the surface ratio, surface area. And let me give you a few minutes to think. Yeah, Jonathan, sorry, I just read your message. Okay, Jonathan, what about the students who cannot do offline exam? Yes, I will wait for you until you come to the campus. Okay, so you will have delayed exam. Okay, and I will prepare the questions for the late students. Okay. So we can maybe draw the cylinder if you want to look. So that's my cylinder. This is H and this will be R. Okay, so volume of cylinder, if you don't remember, it's the base multiplied with the height. The area, circle area multiplied with height. And the surface area is, we have two circle, right? Two circle plus 2 pi r h, right? The one that is covering this peripheral here, the sides. Okay. I'm not sure. Do you still know if in the exam it's actually surface area? Do you know the formula, or you forget? I'm just curious. Do you still remember this one or no? I think you remember, right? This one. Okay. And I think the optimization is if you compare with the related rates. I think related rates sometimes it's difficult to imagine because it's moving, right? But because it's optimization, you just see the object, right? So I think from the words and uh, the problem, so the words in the problem, I think it's easier to be understand this one rather than the related rates, right? Related rates, if you check the question, sometimes it make you confused because A move here, B move there, and then you feel a mix between the question. Okay, but here we just see that we have volume, we have surface area. If we check the questions, the volume is fixed. Okay, so this will be our constraint, okay, and the surface area will be our optimization. Okay, so we need to find the R over H. We need to find when the surface area is minimum. Okay, because we have a constraint here, then we can take this into our considerations, maybe using a different color. So V pi r squared h. And you can take some form if you want. Okay, my preference, I would just take V over R, and then this will be pi r h. Okay. Why? Why I'm taking this? Because when we see this pi r h, I will switch this with this. And if we derive, I think maybe a little bit easier, right? Okay. So how to substitute? First, it depends on the question. Which question is asking? What terms? Okay. And then see the derivative first. And imagine when you derive this, which one is easier for you? And that will be your choice. Okay. So for me, I will use the V divided by R to change this pi R H. Okay. Okay, let's check that out. So surface area will be 2 pi R squared plus 2 V over R. We check the first derivative. So we are making all with the variable R, okay? Because the V, this V is a constant, okay? Is a constant. So we treat it as a constant. So our variable only R. Okay? We check the first derivative, and we get this will be 4 pi R, and then minus 2V R squared. And take this equal 0. And we take this 4 pi R equal to V divided by R squared. And because we know it's a positive, so we can cross multiply. And this will be resulting pi R squared H divided by 2 pi. So R divided by H is half. Okay. Okay, let me give you one example more, but I think we will finish that on the next week, but I will just give you the question first, okay? Find the point on hyperbola xy equal 8 that is closest to point 30. Okay. So first, you need to imagine what the hyperbola looks like. And I think you can just focus on the first quadrant, which is the positive quadrant. Okay? So you can focus the graph on just this part here. Focus on this. Okay. So maybe you can draw the hyperbola. You can draw the hyperbola. Okay. And because you need to find this point 30, you need to find the distance between the hyperbola and then 30. I think you can just draw here, and then you imagine some point on the hyperbola. You can check between this uh, relations, or you can write y equal 8 over x, and you can check with several x to make the function. Okay. And try at your home, and also giving you the other questions related to L'Hopital rule, and maybe also some question about the optimization that you can try. Okay. Okay, while we wait, is there any questions from the students on online students? Okay. So November 30th will be the midterm. Okay. The topic for midterm from chapter 1 to chapter 4. And just skip the part that we are not studied yet. Okay. Skip the some part on the hyperbolic, the exponential growth, decay. That's the part that I'm skipping. The modeling, some modeling part related to physics, chemistry. I'll skip that part. Okay. Okay. If there is no other questions, we can move to the feedback for today. But our feedback is about the L'Hopital. Okay, about the L'Hopital. I just want to make sure you understand the L'Hopital. And probably I will ask about optimization maybe next week. Okay, next week. Okay. So maybe I will give some clue maybe for this one. Okay, giving you some clue. So maybe better to write this in terms of y, 8 over x. Okay, and then use the distance. Okay, the distance formula. The distance formula. Okay, and you can try that at home. Okay, we are moving to the feedback. Yeah, let me stop this. Okay, wait. Okay, wait for the online students. Wait. Okay, 22. Okay, I think we can start. Okay, I think we can start. Okay, start 3, 2, 1. Okay. I hope the time is okay. Okay, 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 good. Okay, okay, a lot of you got the correct answer. Okay, let's next one. We're gonna save it, man. Okay, good, good. Okay, okay, good, good. Okay, 3, 2, 1. Okay, let's start. Okay, okay, tangent, and then with power of cosine x. It's just to check whether you are having a trouble or not with your calculation. Okay, okay, good. Okay, I think if you answered negative, maybe something wrong in the calculation, but if you think it will be impossible to be negative, right? Okay. Okay, still up there. Never gonna say goodbye. Okay, good, good. Okay, last question, last question. Okay, three, two, one. Okay, let's start. Okay, good. 0.5 or half. That will be the answer. Okay. 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 So no, never gonna. Okay. I need your student ID. Okay. Who's this student? Okay. Very funny. I want to know your student ID. And this will be the end of our lecture. So thank you for joining and see you next week. Okay. If you have any, not sure if you have any assignment for your TA, don't forget. Okay. Who is the student? The student. I want to know the student ID. Is this in the classroom? No, no, right? Okay, maybe there's okay. Maybe next week I will check with you. Okay. So this will be the end of our lecture. If you still have some questions, you can ask. We still have time, around 4 or 5 minutes. And thank you for joining. Okay, you can leave the meeting if you're done with the lecture. Oh, okay, okay, okay. Okay, for this classroom, any discussion, any questions you might think you have, or maybe from the uh, practice that I give you, you check some questions. Maybe you feel you need something to discuss. Okay, okay, please let me know. Okay, if there is no questions, that and we finish today's class. Okay.